Hello viewers, welcome back to my channel. Before starting this video, I would like to thank some of my subscribers who has commented and encouraged me for my work. One of them is Ritankar Bhattacharya 2861. Thank you Ritankar for your message and for your encouragement for making my videos. He also said that please sir put more lectures, and also said that sir, I assume that you are from West Bengal, then please teach in Hindi, just a request from a student. But I have answered that I am not fluent in Hindi. Course structure is also in English and the medium is also in Bangla এবং ইংরেজি দুটোতেই আমি চেষ্টা করেছি to put my lectures. Another subscriber coeff6121, he said, please sir keep posting, I understand everything very well. Thank you for your support and encouragement. So in today's video, I will start a new topic, that is laser, under the chapter Optics of MAKAUT B Physics Syllabus, paper code PH101 or 201. Before starting the lecture, I want to convey that in my lecture only theory part has been described. But in semester question paper, not only theory will come, but the full question will consist of theory as well as numerical problem. Only the theory part won't be sufficient to answer the semester question paper. So if you want to join my online theory classes and also numerical problem solving classes, you may contact me through the WhatsApp number and also the Instagram and Facebook direct message given in the background of my screen. There I discuss everything, that means theory, numerical problem, and also previous year question and numerical problem solutions. Everything I discuss in my online classes. So if you are interested, you may contact me. So let us start today's class. This is the MAKAUT syllabus for physics. Under optics chapter, laser syllabus is this much. Now to start laser, few things we have to discuss. The first one is temporal coherence. What is coherence and what are coherent sources? That I have already discussed in my previous lecture of diffraction. The lecture 1 of diffraction I have already discussed everything. I will provide the link for that video in my description section. Now what are coherent sources? The light waves propagating from them should maintain a constant phase difference between them throughout time. That is the property of coherence. Now coherence can be of two types, that is number one is temporal coherence and number 2 is spatial coherence. Now what is temporal coherence? Temporal coherence means a strong correlation or a fixed phase relationship between two electric fields at different times but same location or same position. Temporal coherence means a strong correlation or a fixed phase relationship between two electric fields or the electric fields at one location. Location is same but at different times. Suppose E1 and E2 be two electric fields. Suppose E1 electric field of light wave at point xyz at time t1. Suppose we take position xyz at time t1, the electric field be suppose E1. Similarly, at the same position, according to the condition of temporal coherence, same position xyz, same coordinate, but at different time t2. Let another electric field be E2. Now, if there is a fixed phase relationship or a strong correlation between these two electric fields at different times but same place or same location, then they are said to be a temporal coherence. So, if the phase difference between these two electric fields is constant during the measurement of time, then the waves are said to have temporal coherence. What temporal coherence does? Temporal coherence determines the monochromaticity of light. Monochromaticity means, it is monochromatic means a single wavelength or single frequency. So it determines the monochromaticity of light. Now regarding this we have to discuss another few terms. These are coherence. What are coherence time, coherence length? Coherence time means, the coherence time is denoted as tau c. So the average time in which the coherence property is maintained. That means average time in which the wave can be represented as a pure sine wave or coherence property is maintained, that time period is called coherence time. And coherence time is related to the spectral width or frequency width of that light, that tau c equals to 1 by spectral width, that is delta nu. Spectral width means, suppose for a monochromatic source, due to some defects it is not totally monochromatic, so it contains some spectral lines having a width. Suppose these are the spectral lines of monochromatic waves, and these are the spectral lines, and this is the principal frequency nu naught, and these are the additional frequencies that are generated due to the defects within the source. So as a result of that, a spectral width would be there in the, if you plot a distribution of that intensity distribution of that monochromatic source, there will be a spectral width that is called delta nu, that is called spectral width. The central frequency is the main frequency, that is nu naught. So the coherence time is 1 divided by this spectral width or frequency spread. So this is coherence time. Coherence length, that is denoted as LC, that is coherence length. Coherence length is the propagation distance over which the coherence property is maintained, or the distance over which the constant phase correlation or a fixed phase relationship is maintained, that is called coherence length and denoted by LC. And LC is related to the coherence time as LC equals to C into tau C, where tau C is the coherence time, and LC is the coherence length, and C is the speed of light in free space. So LC equals to C tau C. So temporal coherence is used in Young double slit experiment. That is the one information. So second type of coherence is called spatial coherence. Spatial coherence means a fixed phase correlationship or a strong correlation between electric fields at different position but at same time. So spatial coherence means a strong correlation or a fixed phase relationship between electric fields at different locations. Suppose for a cross section of a laser beam, suppose this is a cross section of laser beam. So if within a cross section of laser beam, so electric fields at two different positions oscillates in a totally correlated way. That means there is a fixed phase correlationship between these two electric fields at different locations but at same time. So spatial coherence is the coherence property of two electric fields at different positions but at the same time. If there is a constant or fixed phase correlationship is maintained between them, then they are said to have spatial coherence. Now spatial coherence is the essential condition for the strong directionality of the laser. That means laser is one of the most important property of laser is directionality property. So if question comes like which coherence property or which type of coherence is responsible for directionality property of laser, that would answer would be spatial coherence. And if question comes like which type of coherence is responsible for the monochromaticity of the laser, the answer would be temporal coherence. So now I will start what is laser. The full form of laser is light amplification by stimulated emission of radiation. So initial letters has been taken and abbreviated as laser. In 1955, Charles Stevens, Nicholas Dassault and Alexander Prokhorov, they got Nobel Prize for inventing lasers. Now what are the characteristic properties of laser? The first characteristic property of laser is directionality property. That means laser is highly directional in nature and spatial coherence is responsible for that directionality property that I have already discussed. As a result of that, laser can be used for surveying as a pointer device. So first property is directionality property. Now there is a term that is called beam divergence of laser, that is given by theta d equals to beta lambda by capital B, where beta is almost unity, this value has almost unity. That depends on type of the light amplitude distribution and definition of beam diameter of the laser. Second, wavelength of the laser is lambda, that is b theta d equals to lambda wavelength into capital D, where capital D is the beam diameter, expression for beam divergence. Second property of laser is it has high power. That means very high intensity or high amount of energy is concentrated over a very small beam cross section or a very small beam area, laser beam area or aerial cross section. As a result of that, laser has very high power, and that leads to application of laser in welding, cutting and laser fusion. So power densities of laser are very high. The third property of laser is this coherence that I have discussed previously. Coherence time is tau c equals to 1 by delta nu, that means delta nu is spectral width and LC by C is tau c. So tau c is the coherence time, that is coherence length divided by speed of light, that is equals to 1 by delta nu. Delta nu is the spectral width, nu naught is the central frequency of the spectrum. Now the fourth characteristics of laser is monochromaticity. Monochromaticity means it is almost single frequency light source, but there is a broadening of that emitted light that is very small, so that it becomes highly monochromatic. That means that broadening that I discussed, that is delta nu, is very small, so that it can be considered as highly monochromatic, having a frequency of central frequency. Now there is a term spectral width divided by central frequency, and that is degree of non-monochromaticity. That is called degree of non-monochromaticity. So delta nu equals to 1 by tau c and central frequency is nu naught. Degree of non-monochromaticity, xi would be 1 by tau c into nu naught. Again tau c is LC by C, so 1 by tau c would be C by LC, so it would be C by LC into nu naught. Degree of non-monochromaticity equals to C by LC into nu naught. Now these are some important expressions. Now what are the laser properties which depends on spatial coherence? The first one I have discussed, that laser is highly directional. That highly directional property is related to the spatial coherence. So it can be used as cutting and lithography or as a pointer. Now what properties are related to temporal coherence? Temporal coherence allows the monochromaticity of the laser source. That means monochromaticity property is due to the temporal coherence property, and also for that laser pulses are produced, or it can be used as femtosecond laser to produce laser pulses or light pulses. So temporal coherence is responsible for this. Next we will discuss about what are radiative transitions. Now the energy level that normally the atoms stay in general or ordinary circumstances are called ground levels. So when an external radiation is incident on those atoms, the atoms gain energy in terms of photons, and those atoms in the ground state level are excited to the upper energy level, which are called excited state or excited levels. After that, atom transit from those excited levels or excited states to the ground state by emitting photons, and this process, in which photons are involved during the de-excitation of atoms or molecules from upper excited level to the ground level, they are called radiative transition. So radiative transition means atoms transition from excited to ground level by emitting photons in terms of radiation of light. Now in 1917, Einstein predicted that atoms in an excited level can make a radiative transition to the ground level by two processes, or radiative transition process may occur in two different procedures. Number one is called spontaneous emission and second one is called stimulated emission. Now what are spontaneous emission? When transition of those atoms from the excited level to ground level occurs without any presence of external radiation energy density or in presence of external radiation, then they are called spontaneous emission. And in case of spontaneous emission, the rate equation, that means the rate of transition from of the atoms or molecules from excited level to ground level is independent of the incident energy density. That means it doesn't depend on externally incident radiation. That type of transition is called spontaneous emission or spontaneous emission transition. So spontaneous emission means when a transition of atom is not caused by presence of electromagnetic radiation and the time rate of transition is independent of energy density of the radiation. That means d and dt is the rate of transition that is independent of energy density u omega, that is independent of energy density. Then that type of emission is called spontaneous emission. Next, what is stimulated emission? In case of stimulated emission, the radiation or the radiative transfer is caused in presence of external electromagnetic radiation, and the time rate of transition, that means d and dt, is directly proportional to the energy density of the incident radiation. Not only that, but also the radiative transition or the radiative emission, that will have same properties, that means same frequency. Say if they have polarization, then that would be same state of polarization and same phase as that of the incident radiation. তার মানে কি, স্টিমুলেটেড এমিশনের ক্ষেত্রে রেডিয়েটিভ ট্রানজিশনস হবে ইন প্রেজেন্স অফ এক্সটার্নালি ইনসিডেন্ট রেডিয়েশন, এবং টাইম রেট অফ ট্রানজিশন যেটা dn/dt, দ্যাট উড বি প্রপোর্শনাল টু দ্য এনার্জি ডেন্সিটি অফ দ্য ইনসিডেন্ট রেডিয়েশন। অ্যান্ড দ্য রেডিয়েশন, দ্য স্টিমুলেটেড রেডিয়েশন যেটা পাওয়া যাবে, সেই স্টিমুলেটেড রেডিয়েশন যেটা পাবো, দ্যাট উইল হ্যাভ সেম প্রপার্টি, তাদের সেম প্রপার্টি থাকবে অ্যাজ দ্য ইনসিডেন্ট রেডিয়েশন। মানে তাদের যদি ফেজ ইনসিডেন্ট রেডিয়েশনের যা ফেজ স্টিমুলেটেড এমিশনের রেডিয়েশনের সেম ফেজ হবে, তারা সেম ফ্রিকোয়েন্সির হবে, এবং যদি তাদের পোলারাইজেশন থাকে তাহলে পোলারাইজেশন প্রপার্টিটাও সেম হবে। অ্যান্ড অলসো স্টিমুলেটেড এমিশন emitted light will also propagate along the same direction as the incident radiation. তার মানে stimulated emission means it is caused by the presence of an electromagnetic radiation of proper frequency and the time rate of transition, that is d and dt. Stimulated emission, it is written like this: d and dt, stimulated emission, that would be proportional to the incident, directly proportional to the incident energy density of the radiation, that is u omega. Thus stimulated radiation has the same phase, same frequency and same state of polarization as that of incident radiation, and also stimulated radiation propagates along the same direction as that of incident radiation. So these are two types of radiative transitions, spontaneous and stimulated emission, and their differences. So this is the diagram, that is spontaneous emission. That means from upper level 2 to 1, the energy or radiative energy has been shown here, and that will occur in absence of external incident radiation. But here this is the external incident radiation, and the emitted radiation will have same property as that of incident radiation, and it will occur in presence of external radiation, and dn/dt, that would be proportional to u omega, that is energy density of the incident radiation. So these are the difference between spontaneous and stimulated emission. Next, we will establish a relationship that between Einstein A and B coefficient. That also came as a semester question in MAKAUT 2020. Here we will discuss about the relationship between Einstein AB coefficient, and that is very much important in laser. For that, let us consider some atoms of a material have two energy levels, E1 and E2. Suppose E1 is the ground state energy level of that material where the atom stays in normal conditions, and E2 be the excited state level. So after incidence of radiative energy, external radiation, suppose this is the external radiation. So atoms in the ground level will absorb the incident radiation energy, and they will go to the upper excited level, that is E2. And suppose in normal condition N1 be the number or atoms per unit volume at energy level E1, and N2 be the atoms per unit volume at energy level E2. That means N1 and N2 are the populations of level E1 and level E2. So now the population of E2, this one, can be changed by three processes. তিনটে প্রসেসে আমরা population of N2 by excited state population কে আমরা চেঞ্জ করতে পারি। Number one is absorption process or absorption radiation. That means the atoms in the level E1 will absorb energy and they will go to E2, and thus population of E2 would be increased. So due to that absorption process, the rate of change of population at N2, that would be dN2 divided by dt, and the process name is absorption. That's why suffix abs. So dN2 by dt absorption, that would be proportional to incident radiation energy density U suffix U omega. Suppose the incident energy radiation has a density of U omega. Omega is the angular frequency of the radiation and U omega is the density, energy density of the radiation. So in case of absorption process, dN2 by dt, the rate of increase or rate of change of population at N2 due to N1 would be proportional to U omega and population of E1, that is N1. So absorption rate, that would be proportional to incident energy density and also proportional to the population of N1. So this is the rate of change of population in N2 due to absorption. And if we remove the proportionality symbol, then we have to put a proportionality constant, and that is given as B12, where B12 is proportionality constant. Let us consider this equation as equation 1. So this is equation 1. So after reaching the level E2, from E2, two processes of emission will occur. One is spontaneous emission and another one is stimulated emission. So in case of spontaneous emission, the rate of change of population at N2 due to spontaneous emission, that rate would be dN2 by dt suffix spontaneous emission. That would be independent of energy density U omega. So that would be just proportional to the population at E2, that is N2. So if we remove the proportionality constant, we can write as, that is dN2 by dt spontaneous emission, that would be equals to minus A21, where A21 is a proportionality constant. Here I want to discuss that why this negative symbol came, and also why I am writing this suffix as 21 for previous case 12. Here the negative symbol comes due to the decrease of population of E2. That means from upper level, due to spontaneous emission, the population of E2, that means N2 is decreasing due to spontaneous emission, and that is why I have put a negative symbol before that proportionality constant. And the suffix 21 means it is transition is from level 2 to level 1, means excited level 2 to ground level 1. That's why I have written is 21. Similarly, in previous case, in the case of absorption of radiation, the proportionality constant was written as B12. Why 12? Because the atoms are leaving energy level 1 and reaching energy level 2. That's why I have written B12. And here the sign is positive because population of N2 is increasing. That's why there is only positive sign. But here in case of spontaneous emission, there is a negative sign, as population of N2 or E2 decreasing. So we take this equation as equation 2. Now in third case, that is case of stimulated emission. So in case of stimulated emission, the transition will occur from E2 to E1. Here the rate equation would be dN2 by dt stimulated emission, which would be proportional to energy. Stimulated emission occurs in presence of external energy density, so U omega into, that would be also proportional to population of E2, that is N2. And if we remove the proportionality constant, then we can write it as dN2 by dt stimulated emission equals to minus of B21 into U omega N2, where negative sign is due to the decrement or decrease of population at E2, and B21 means a proportionality constant that is due to the transition from 2 to 1. So my B21 is another proportionality constant. যেহেতু এটা ট্রানজিশন হচ্ছে 2 থেকে 1 এ তার জন্য BT1. So this is the rate equation for stimulated emission, and we take it as equation 3. So from these three equations, the three proportionality constants, that is B12, A21 and B21, are called Einstein's coefficient. So these three proportionality constants are called Einstein's coefficients in laser. So now we have to establish the relationship between these Einstein coefficients. Now from the three equations, from absorption, spontaneous emission and stimulated emission, that means equation 1, equation 2 and equation 3, the net rate of change of population or net change of population into, that would be equation 1 plus equation 2 plus equation 3. So if we add these three equations, we will get the net change of population, that is called dN2 by dt, that is the net change or net result or net change, the effective change in population, that would be equation 1 plus equation 2 plus equation 3. That means B1, that if we add those three equations, we will get dN2 by dt, that would be B12 u omega into N1, this would be N1, plus minus A21 N2 minus B21 u omega N2. So at thermal equilibrium, this dN2 by dt effective or resultant would be 0. So from there we will get this term 0, or B12 u omega N1 minus A21 N2 minus B21 u omega N2, that is equals to 0. Or if we take common u omega, then in bracket it would be B12 N1 minus B21 N2, that would be equals to A21 N2, or u omega, the energy density would be A21 N2 divided by B12 N1 minus B21 N2. If we divide numerator and denominator both by N2, then we will get A21 divided by B12 into N1 by N2 minus B21. So this is the expression for energy density at thermal equilibrium. But in thermal equilibrium, N2 and N1 follows Boltzmann law, which is N2 equals to N1 into e to the power minus of energy difference between E2 to E1, that is, suppose we take it as delta E divided by KT, where delta E is equals to energy difference between E2 to E1. Now as it is N2 equals to N1 into the power minus delta E by KT, so it will always be N2 very less than N1 in ordinary circumstances. So N2 would be very less than N1 in normal circumstances or normal case. Obeyed by Boltzmann law. That means population of N2 would be very less than N1 in ordinary circumstances. We take that energy difference delta E be h into nu. H is the Planck constant, nu is the frequency, or we can write it as h cut omega. where nu equals to omega by 2 pi and h cut equals to h Planck constant divided by 2 pi. So we can write this equation as n2 equals to n1 e to the power minus h cut omega by k. So n1 by n2 would be n1 divided by n2, that would be just e to the power h cut omega by kt. Now if we put this equation or this value n1 by n2 here, we put this value here, so we will get the energy density as, so energy density we will get u omega, that would be A21 divided by B12 into to the power h cut omega by kt minus B21, or if we divide both numerator and denominator by B21, we will get A21 divided by B21 whole divided by B12 divided by B21 e to the power h cut omega by kt minus 1, and we take it as or name it as equation 4. Now if we compare this equation with Planck's law of blackbody radiation, which I will teach in quantum mechanics part later. According to Planck's blackbody radiation, the energy density expression is given by u omega, that is given by h cut omega cube n cube divided by pi square c cube into 1 divided by e to the power h cut omega by kt minus 1. This is according to Planck's law of blackbody radiation. So expression for Planck's law of blackbody radiation. So we take it as equation 5. So if we compare 4 and 5, 4 and 5, what we get? So this equation and this equation, if we compare, we will get B12 by B21 equals to 1. That means coefficient here is 1 and here coefficient is B12 by B21. So B12 by B21 equals to 1, and similarly another term, this term would be equal to A21 by B21, or A21 divided by B21, that would be equals to h cut omega cube n cube by pi square c cube. Here in Planck's law of blackbody radiation, h cut is h by 2 pi, Planck constant by 2 pi, omega is the angular frequency of the radiation, n is the refractive index, pi c is the velocity of light in free space. So all those terms, all those symbols has their own meaning. So from here, if we compare this blackbody radiation energy density with the energy density from what we obtained, we will get B12 equals to, that means from here we will get B12 equals to B21, and secondly we get A21 by B21 equals to h cut omega cube n cube divided by pi square c cube, or from here we can write A21 equals to h cut omega cube n cube divided by pi square c cube into B21, where B21 is also again B12. Finally we get the relation between those Einstein coefficient is this one. So A21 by B21 equals to h cut omega cube n cube by pi square c cube, B12 equals to B21 equals to A21 pi square c cube by h cut omega cube n cube. So these are the relation of Einstein's coefficient, and this is very important question for MAKAUT B Tech physics semester. Now we will discuss about what is population inversion. Now as we know that three processes are occurring at the simultaneously, that is absorption process, spontaneous emission process and stimulated emission process. Now the condition for better probability of stimulated emission depends on two factors, that is number one is ratio of probability of stimulated emission to absorption and secondly is ratio of probability of stimulated emission to spontaneous transition. That means first condition is dN2 by dt stimulated emission divided by dN2 by dt absorption. This is the first condition. The second condition is to get better probability of stimulated emission. Second condition is dN2 by dt stimulated emission by dN2 by dt spontaneous emission. That ratio, that two ratios or over this or on these two ratios, the probability of stimulated transition depends. Now from the ratio of equation 3 by equation 1, that means the first condition, this is equation 1 and this one is equation 3. So equation 3 divided by equation 1, and if we take the negative sign in the left hand side, then it will get d minus of dN2 by dt stimulated emission divided by dN2 by dt absorption transition. That would be equals to, we make the ratio 2 1 N2 u omega divided by B12 N1 u omega. Now as B12 equals to B21, so this will cancel, u omega will cancel, then only that would be N2 by N1. So rate of transition stimulated emission by rate of transition of absorption, that would be N2 by N1, and which is also equals to e to the power minus h cut omega by kt according to Boltzmann law. So N2 will be always less than N1. So excited state population would be very much less than ground state population. So in normal condition or normal circumstances, in normal condition N2 is very less than N1. Our population of excited level is very less than ground level. So now to achieve larger probability of stimulated emission, N2 should be very much greater than N1. Stimulated emission probability বেশি করার জন্য আমার প্রথম কন্ডিশন অনুযায়ী কি করতে হবে, population of N2 should be very greater than population of N1. গ্রাউন্ড স্টেট লেভেলের থেকে এক্সাইটেড স্টেট লেভেলের পপুলেশনটা অনেক বেশি হতে হবে। And this is done by an artificial means, an artificial non-equilibrium process. We can achieve that, and this process is called population inversion. Now what is population inversion? To achieve higher probability of stimulated emission over absorption, the population of N2 or higher level, excited level should be very greater than the population of ground level, and this cannot be done in normal circumstances. An artificial means or by an artificial process, which is also non-equilibrium process. So by an artificial non-equilibrium process by which the population of the excited state level is made higher than that ground state level is called the population inversion. And it came as a question in 2023 that what is population inversion and why is it essential for sustainable laser action. So population inversion is to achieve larger probability of stimulated emission. Population of higher level N2 should be very greater than N1, which is attained by an artificial non-equilibrium process, and this process is called population inversion. Then one question arises. The question is, does Maxwell-Boltzmann law fails in case of population inversion, or is there any fault in Maxwell-Boltzmann law? এটা যদি হয় তাহলে একটা কি হচ্ছে, N2 আমরা greater than N1 করে নিচ্ছি by the process of population inversion. We are making N2 greater than N1, but in ordinary circumstances always according to Boltzmann law N2 would be very less than N1. তাহলে কি হচ্ছে, তাহলে কি আমরা বলতে পারি যে Maxwell-Boltzmann law invalid or fails in this case, or there is a fault in Maxwell-Boltzmann law? The answer is no. So there is no fault in Maxwell-Boltzmann law because Maxwell-Boltzmann law
is valid for only equilibrium case or equilibrium condition. So Maxwell-Boltzmann law is valid for equilibrium condition, but here we are dealing with an artificial non-equilibrium condition, non-equilibrium state. So here Maxwell-Boltzmann law is not valid. Maxwell-Boltzmann law is only valid for equilibrium condition. So আমরা বলতে পারি যে না Maxwell-Boltzmann lawটা invalid নয় বা এর কোনো ফল্ট নেই। As we are inserting a non-equilibrium artificial process to introduce population inversion, so here Maxwell-Boltzmann law cannot be applied. So that artificial non-equilibrium process to achieve population inversion is done by introducing a metastable state. একটা নতুন স্টেট যেটা একটু নতুন একটা এনার্জি লেভেল in between one energy level 1 and energy level 2, E1 and E2, we will introduce one state that is called metastable state, and that artificial non-equilibrium process for population inversion is done by introducing that metastable state. Now if we make a ratio of equation 3 by equation 1, we will get minus dn2 by dt stimulated emission to dn2 by dt spontaneous emission. That would be equals to b21 u omega divided by a21. That means stimulated emission rate divided by spontaneous emission rate. If we take the negative sign in the left hand side, then we will right hand side we will get b21 u omega a21. From here we can tell that, so from here we can say that to achieve stimulated emission rate very much higher than spontaneous emission, either of them or both of them should be satisfied. The conditions are that b21 ratio of b21 to a21, that is b21 divided by a21 should be very high, greater than 1, and the energy density u omega of the incident energy density u omega should be very high. So to make probability of stimulated emission very much higher than spontaneous emission, we have to make the incident energy density very high, and secondly b21 by a21 ratio should be very greater than 1. Condition 1, that means b21 by a21 ratio can very greater than 1, that condition can be achieved by choosing a metastable state between E1 and E2. Now the metastable state has a very interesting property, that is in case of normal ordinary excited state, the lifetime of the atoms are 10 to the power minus 8 second. তারা 10 to the power minus 8 second অবধি ওই অর্ডিনারি এক্সাইটেড লেভেলে অ্যাটমসগুলো স্টে করতে পারে। বাট ইন কেস অফ মেটাস্টেবল স্টেট they have a lifetime of 10 to the power minus 3 second. That means ordinary excited level থেকে 10 to the power 5 times higher lifetime. So in case of metastable state, they have a lifetime higher than the ordinary excited state by 10 to the power 5 times. So atoms will reside there for a longer period of time. As a result of that, population inversion at EM, that is metastable state, is achieved. Metastable state has a property that normal lifetime of atom in ordinary excited level is 10 to the minus 8 second, but in case of metastable state it is 10 to the minus 3 second. So 10 to the power 5 times higher lifetime the metastable state has. As a result of that, atoms will stay longer time at EM, and EM will exceed the population of ground level, that is E1. So as a result of that, population inversion will be attained. So this is how population inversion is attained, by introducing a metastable state. So these are very important properties and these are very important conditions for your semester paper. And what are population inversion, what are metastable state and their characteristics. Now once the population inversion is achieved by introducing a metastable state, light amplification will take place. Light amplification means more atoms in the EM level, excited metastable level, will de-excited to E1 by emitting photons of energy h cut omega, which is equals to EM minus E1. So more stimulated emitted photons will be added to the incident radiation. So these photons created from radiation stimulated emission due to EM to EI, these photons will be created and they would be added to the incident radiation. As a result of that, incident radiation energy will be very high or light amplification will take place. So thus photons will be added to the incident radiation instead of photons being removed from the incident radiation, thus causing a light amplification. And after completion of this population inversion and light amplification, the lasing action takes place. So lasing action will take place after this, means after attaining population inversion by introducing a metastable state, they will start stimulated emission and light amplification will take place. After that, finally lasing action will start from that material. তাহলে এইভাবে আমরা লেজিং অ্যাকশন বা লেজার আমরা প্রডিউস করতে পারি from a material. So another question comes, that is lasing action possible with two level system? Lasing action ki two level system is possible? Answer is no, because for two level system, there will be no population inversion. So in normal circumstances, the ground level population will be very much higher than the excited level. So we have to introduce a metastable state to create population inversion. So until or unless we introduce a third state between 1 and 2 metastable state, we cannot get lasing action. So at least 3 level system we require to produce laser. So this is the end of first lecture on laser. See you in the next video. Till then, bye.